Welcome to problem solving session 5 for the course Computational Fluid Dynamics in NPTEL by Professor Sreenivas Jayanti. So today we will move on to solving few of the assignment problems from week 5. If there is any doubt, please feel free to stop and ask questions. Thank you. So these are all the syllabus of the course, and we are in week 5 where we are focusing on finite difference approximation. Till now we have solved the calculation of flow in a rectangular duct, triangular duct, and derivation of equations for the fluid flow, and also the incompressible flow and the boundary conditions associated with it. So we'll see the problems today. So this week, the problems mainly focus on grids and mainly finite difference approximation and how it is termed and how it is derived and how to solve the problems associated with it. So these are all the four figures given in for the problems associated with week 5. From this, what are all the things that you can infer from this? Like there are four different meshes, right? If any one of you have any interpretation that is from these figures, please feel free to say. You can unmute yourself and say. So yeah, these are all different grids, sizes, and what are all the grids? Number of various grid points are basically mentioned over here, and that's it. Like, and all these are uniform meshes, whereas this figure 4 alone is unique in the way that it is denoting a non-uniform mesh. We'll see what are all the problems that are asked from these. Before that, we'll just have a quick recap of the discretization. Mainly the discretization, we are deriving it from the Taylor series. In Taylor series, we are getting an expansion of variable in terms of all these things. So if we want to know the value of the function f of x plus delta x, and we know these delta x, we can use this formula to know the value at f of x plus delta x. If we know the value of f of x at x and the differentiate, like derivative of f of x at x and the second derivative followed by nth derivative. The main thing to be noted is the accuracy depends on how many terms we are including in the Taylor series expansion while using different schemes. If we are going when converting the partial differential equation, partial derivatives to algebraic expressions, we are using three different schemes. One is forward, backward, and the central difference schemes. In forward scheme, as the name suggests, we are using the current point and the point next to it. In backward difference, we are using the point, current point, and the point behind it. Whereas in central difference, it is kind of like we are taking two different points and using it as central difference scheme. So we'll see how it is derived from the Taylor series. Like a quick recap, if we take this term that side and divide it by delta x, we will get the Taylor series. That is dou f of dou f by dou x at point x is equal to f of x plus delta x minus f of x at x by delta x. That is, all these three terms remain, and we are eliminating all these terms. So when this term goes over that side, and the entire expression is divided by delta x. So these are the terms that are truncated. If it is divided by delta x, we'll get only one delta x remaining over here. In that sense, we will be using the term, it is first order accurate, since we are having only one delta x. In that case, it is first order. So next we will see what is the backward difference. If it is expanded in terms of f of x minus delta x, and it is f of x at x, here we are using minus in the odd even places, like dou f by dou x at delta x plus dou square f by dou x square delta x square by 2 factorial. Again it would be like minus. It is like when n is odd, we will be getting a minus, like dou f by dou x and dou cube by dou cube f by dou x cube. In all these places, we will be getting a one negative sign if we are using Taylor series to expand it to backward f of x minus delta x. So the backward difference formula arrives by taking similar to this approach, where we are taking three different the first three terms and taking the f of x minus delta x to that side and using delta x. So since similar to the last approach, the order is delta x, so it is first order accurate. But in central difference scheme, what we will be doing is, we'll be taking this equation and this equation, and we'll be subtracting both these equations. So what we'll be getting, f of x plus delta x minus f of x minus delta x. So the first term in both of these are positive signs, so they'll get cancelled out. Whereas here we'll be getting 2 dou f by dou x at x delta x. And when we want to get dou f by dou x, we will be getting f of x plus delta x minus f of x minus delta x by 2 delta x. And the order how we will be finding it out is, it would be like, since we are subtracting both the equations, this term is positive in both the equations, so it will get cancelled out. The next term to this is dou cube f by dou x cube in at x by delta x cube by 3 factorial. That term would be there. That term, since it is in third position, n is 3, we would be having minus. So here it is minus and here it would be plus. So plus and minus, when we are subtracting, it would add up and that term would be remaining. When we are dividing the entire equation by delta x, we would be getting delta x square. So the order of this central difference scheme is second order accurate. In this manner, we can tell what the order of accuracy of each equations are. Next, we now move on to the problems for this week. So this is question 1. Question 1 is associated with figure 1. In figure 1, the dark thick line indicates the boundaries of the computational domain. Which of the following is a Dirichlet boundary condition on the side AB? It is U is equal to 0, 0 shear stress and adiabatic boundary. Let's see what are all the options available. First one is 1, that is U is equal to 0, and second is 1 and 2, and third option is 1 and 3, and fourth is 1, 2 and 3. This is the thick line that is indicating the boundary of the computational domain. So which of the following is a Dirichlet boundary condition? First, before knowing that, we should know what is Dirichlet boundary condition. When we are denoting the values of a variable at the boundary, we know, we say that to be Dirichlet boundary condition. The other boundary condition, what is the other boundary condition? Can anyone say that? There are two types of boundary conditions. One is Dirichlet boundary condition and the other one is, yeah, it is Newman boundary condition. Newman boundary condition, we denote the value of a derivative of the variable, that is dou u by dou x, kind of that. If we are denoting the value of that, that is known as Newman boundary condition. So since they are asking for Dirichlet boundary condition, the answer to this is u is equal to 0. So it is option 1. We'll see what is the answer. The answer is option 1. That is, the dark thick line indicates the boundaries of the computational domain. Which of the following is the Dirichlet boundary condition on side AB? For this side, the Dirichlet boundary condition is u is equal to 0, where we are specifying the value of a particular variable. I hope this is clear. We'll now move on to question number 2. In question number 2, we are shown this figure. We'll see what the question is. Which of the following statements is true about computational molecule shown in figure 2? Before moving on, we'll just see what it basically is denoting. It is like this midpoint is I comma j, and this is moving in y direction is j plus 1, j minus 1, and it is I minus 1, and this is I plus 1 when we are moving in the x direction. So, and this few and a few boundary points are marked, or a few points are marked, they are not specifically. So we'll see what the question is. Differencing of Poisson equation as this computational molecule. Central differencing of Laplace equation as this computational molecule. And the magnitude of the diagonal coefficient is greater than the sum of the magnitudes of and the magnitude of the diagonal coefficient is greater than the sum of the magnitudes of off-diagonal coefficient in the same row for an interior point. And the options given for this question is option 1, option 1 and 2, option 1 and 3, and option 1, 2 and 3. So basically, this is a computational molecule is given for which of the following statements are true. That is the question asked. The first one is central differencing of the Poisson equation as this computational molecule. We can see that it is I comma j minus 1, I minus 1 comma j, and I comma j plus 1, and I plus 1 comma j. So it is covering these molecules. So the central differencing scheme is true. So the option 1 is true. And in option 2, it is given that the central differencing of the Laplace equation has this computational molecule. This is also true. The magnitude of the diagonal coefficient is greater than the sum of the magnitudes of the off-diagonal coefficients in the same row for an interior point. This is not true, or we cannot estimate it. So basically the 1 and 2 options are correct. So answer to this question is number 2. We'll see if it is the correct answer. So answer is 2. So we'll move on to question 3. In question 3, this type of figure is given, and similar it has 4 points A, B, C, D at this is I comma j, so it is 1 point decreasing here, 1 point decreasing here, and this is at this corner or the boundary. So we'll see what the question is associated with this problem. With respect to figure 3, for discretization of which of the following at I comma j may we get one or more of the corner points A, B, C, D. Dou square u by dou x square plus dou square u by dou y square, or dou square u by dou y square. In option 3, it is dou square u by dou x dou y. And in option 4, it is dou square u by dou x square minus dou square u by dou y square. So, for discretization of which of the following points, we may get one or more of the coordinate points. So, it is asked that there are 4 discretization options given, for out of which we should see, identify which A, B, C, D, which of the following things are including those points. That is I plus 1 comma j minus 1, I plus 1 comma j minus, I minus 1 comma j plus 1, and so on, like these A, B, C, D. That is I plus 1, j minus 1, I minus 1, j minus 1, I minus 1, j plus 1, I plus 1, j plus 1, and I plus 1, j minus 1. So we'll see, to identify that, we should be first writing it in the discretized form. Then we can identify which of the following points would be seen. Dou square u by dou x square at I comma j, it is given by u I minus 1 j minus 2 u I j plus u I plus 1 j by delta x square. It is of the order of second order accurate. Similar manner, if we write it for dou square u by dou y square at I comma j, it is uij plus 1. Since we are moving with the y domain, it is uij plus 1 minus 2uij plus uij minus 1. The things to be noted is, here we are moving in the x direction, so it is I minus 1, I plus 1. Whereas here we are moving in the y direction, so it is j plus 1 and j minus 1, and it is second order accurate. It is divided by delta y square. So what are all the options given? It is dou square u by dou x square plus dou square u by dou y square, dou square u by dou y square, dou square u by dou x dou y. This is a mixed derivative, and these are all, like we can see that dou square u by dou y square is not the option, because it is only going u I j plus 1 or u I j minus 1 I j. It is not having I plus 1 j plus 1. All those were the terms that was asked, like a b c d. So we'll see, second option is definitely not there. Uij plus 1, it is not there. So we'll see the mixed derivative, dou square u by dou x dou y. Mixed derivative is giving that ui plus 1 j plus 1 minus 2 ui plus 1 j minus 1 minus ui minus 1 j plus 1 plus ui minus 1 j minus 1 by 4 delta x delta y plus, it is of the order of second order accurate with x, second order accurate with y. So if we are adding first and the second equation, dou square u by dou x square plus or minus dou square u by dou y square, that is the option 1 and 2, we will be getting two different terms, where in both of the terms the corner points were not included. Only in the mixed derivative the corner points were included. So it is option 3, that is dou square u by dou x dou y. That in only in the dou square u by dou x dou y we are having corner points A, B, C and D. If I hope question 3 is clear, we will now move on to question 4. In this question 4, a grid is given, I mean a different meshing is given, where it is I minus 2, I minus 1, I plus 1, I plus 2 in the x direction. So before moving on to the question, can anyone say what is the unique thing, I mean not unique one, what is the different approach that can be seen from this figure that was not seen in earlier cases? Um, okay, so basically in this we can see that the spacing is different in between each grid points. That is, from here it is smaller and towards this it has become larger one. So this is known as non-uniform meshing. It is therefore different from the uniform meshing that we have seen in the previous problems. So we'll see the question over here. Which of the following option is correct with respect to the grid shown in figure 4? It is a non-uniform grid. Finite difference method cannot be used for this grid. Finite volume method cannot be used for this grid. And the option is, for out of these three statements we have to choose which one is correct. Answer is option 1, 1 and 2, 1 and 3, 1, 2 and 3. So before moving on to the options, we'll see which of the following statements is correct. It is a non-uniform grid, that is correct. It is a non-uniform grid because the sizing is different in each steps. Finite volume method cannot be used for this method, not true, because we can use finite difference method cannot be used for this grid. It is not true because we can use finite difference method, but the procedure would be slightly complicated with delta x varying at each step. And the next one is finite volume method cannot be used for this grid. This is also not true because we can use finite volume method also. So the only statement that is correct is first statement, that is it is a non-uniform grid. Answer is option 1, that is first statement only is correct. Now we'll move on to question 5. In question 5, a similar grid is given, that is figure 3. We'll see the question. Now what is asked in this question? If we write the Taylor series expansion for f of p about point I comma j in figure 3, then the third term in the expansion is given by. So if f of p about point ij is written, then the third term in the expansion is given by what? Before moving this, we need to see few things like it is f of p and ij. Between p is here, whereas I comma j is here. Between them, two grids are there, two meshes, two cells are there in horizontal direction. So it is like it is not delta x. It is 2 times delta x. The thing we should observe from this figure before looking into the problem first. So if we write a Taylor series expansion for f of p about point I comma j in figure 3, then the third term in the expansion is given by option 1, it is 2 dou square f by dou x square at p into delta x square minus 2 by 3 dou cube f by dou x cube at I comma j delta x cube minus 4 by 3 delta cube f by delta x cube at p in times delta x cube and 2 times dou square f by dou x square at I comma j times delta x square. So it is given that answer is option 4. So what is Taylor series expansion? That is f of x plus delta x is equal to f of x plus dou f by dou x into delta x plus dou square f by dou x square into delta x square by 2 factorial. So the middle two options are not there because if we write it, the answer to this is involving in the second derivative. So it must be either option 1 or option 2. It is dou square f by dou x square into delta x square by 2 factorial. Here delta x is 2 times of delta x. So it is 4 times delta x square by 2 factorial. It is so 4 by 2 gets cancelled and only 1 2 remains in the numerator. And it is asked like what is the difference between option 1 and 4? Option 1 is given at point P and option 4 is given at point I comma j. Since the question mainly focuses on asking about point I comma j in figure 3, the answer to this question is option 4, that is 2 times dou square f by dou x square at I comma j into delta x square. So answer is f of x plus 2h is equal to f of x plus 2h times h f dash of x plus 2 times h square f double dash of x. So when we are ignoring all other terms, it is of third order accuracy, and this 2 h square only comes over here, like h is change here, like it is 2h, so 4h square by 2 factorial. So 2 and 2 gets 4 gets cancelled and it becomes 2. We'll now move on to question 6. I guess someone joined. Okay. Yeah, now we'll see question 6. If anyone is having any trouble in understanding any problems or any other issues you are facing during the live session, please feel free to unmute yourself and say, or else even if you are having any doubts or any queries or anything you are not understanding at the moment, please feel free to stop and say at any moment. Or else you can ask the questions at the end of the session too, that is not an issue. Okay, we'll now see the question number 6. D square f by dx square is equal to minus f of I plus 2 plus 16 f of I plus 1 minus 30 f of I plus 16 f of I minus 1 minus f of I minus 2 divided by 24 delta x square is an approximation of what order of accuracy? So few things are given. They have given an equation and asked what is the order of accuracy of this equation. That is d square f by dx square is equal to minus f of I plus 2 plus 16 f of I plus 1 minus 30 f of I plus 16 f of I minus 1 minus f of I minus 2 by 24 delta x square is an order approximation of what order of accuracy. So basically this is a say 5 points are given for this and ask for the number of order of accuracy, and this is a second order derivative. And we do not know what scheming is used. So we'll see the first option is option 2 and second is option 3 and third is option 4 and fourth is none of the above. So if we blindly go by this, n is equal to p plus q minus 1 and n is 5 points minus 2, it would be 3 or 4. But we do not know, so we'll see what the equation should be. It is none of the above because we'll see various equations in different order of accuracy, and we'll see it is second order accuracy center difference scheme. For this like we need to get the f double dash of x through central difference scheme, forward difference scheme and backward difference approximations. So all the things are given for second order and fourth order order of accuracy. So it can be seen that 5 points were given. So obviously this was not the case. And in forward differencing scheme also only 4 points are given. X plus delta x, x plus 2 delta x, x plus 3 delta x. So forward approximation is also not true. And in central difference scheme it is x plus 2 delta x plus delta x and x minus delta x and x minus 2 delta x. So 5 points are given but it is 12 delta x square and it is not 24 delta x square. So even though all other coefficients like minus 1, 16, minus 30, plus 16, minus 1, everything else is matching, this is not an fourth order accuracy. Order of delta x power 4, this is not true because one term is different. So we know in this question the order of accuracy was asked for the second order differential scheme. So we have seen the different order of accuracy like second order and fourth order accuracy equations and saw that for forward differencing scheme, backward differencing scheme and central differencing scheme, and we identify the number of points and saw it is not matching with all other schemes, only with it was somewhat matching with the fourth order central differencing scheme, but it was not 24 delta x square, it was 12 delta x square as can be seen from this equation. So the answer to this problem is none of the above. I hope this is clear. Now we'll move on to question 7. For what value of P is the following a second order accurate approximation? So it is given that d cube f by dx cube is equal to minus 3fi plus 4 plus 14f of I plus 3 minus 24f of I plus 2 plus p of f of I plus 1 minus f of phi f of I divided by 2 delta x cube. So this is a third order derivative and it is given it is second order accurate approximation. So from this it can be seen that for third order derivative and second order accurate approximation, what is the value of P? We compare it with the known equation, it is 3 14 minus 24 and P is 18. So from this we can say it is P is 18. Option 1 is 12, option 2 is 14, option 3 is 16, option 4 is 18. So the answer to this problem is option 18. But do any one of you know how to get the value of P? Not by directly seeing it or anyone, there is a long procedure to it. If any one of you knows just few steps also, it is fine. You can just say. Please interact, then only the session will be more interesting. Okay, fine. Now we'll just see how we can arrive at the conclusion that P is 18 without directly looking at the problem is. Just listen with attention because it is a long procedure and we'll see that. So answer to this problem is option 4, that is answer is option 4, that is 18. So we'll see the things. So it is first we'll identify what are all the points that are considered while solving this equation. That is f of I plus 4, f of I plus 3, f of I plus 2, f of I plus 1, f of I and delta x cube. So we'll use all these f of I plus 1, f of I plus 2, f of I plus 3, f of I plus 4. So by using Taylor's approximation, we'll first derive or expand these things using Taylor's approximation. We know that f of x plus x plus 1 is f of x plus f dash of x delta x, f double dash of x delta x square by 2, and f of f triple dash of x by delta x cube by 3 factorial plus f of fourth dash power of x into delta x power 4 by 4 factorial, that is f of x plus delta x. So here we are denoting that f of x plus delta x as f of x I plus 1. So it is step size is 1 in this equation, so it is f of x plus f dash of x delta x plus f double dash of x delta x square by 2. This is 2 factorial, guys, and it is f triple dash of x into delta x cube by 3 factorial, f fourth dash power of x by delta x power 4 by 4 factorial. And in a similar manner, we'll be writing it for f of x plus 2, x I plus 2, that is f of x plus 2 delta x. This is what we saw in problem that was 2 problems ahead and 2 problems before. F of x plus 2 delta x we have used in a problem. So similarly, it is f of x plus 2 delta x is equal to f of x plus f dash of x 2 times delta x, f double dash of x 2 delta x the whole square, that would give 4 delta x square by 2 factorial. 4 and 2 would get cancelled, it is 2, and f triple dash of x 2 delta x cube by 3 factorial, that is 2 cube is 8 delta x cube by 3 factorial. F fourth dash of x is equal to 2 delta x power 4, that is 2 power 4, it is 16 delta x cube by 4 factorial. In a similar fashion, we are writing it for f of xi plus 3, that is f of x plus 3 delta x. It would be f of x plus f dash of x 3 delta x plus f double dash of x 3 delta x the whole square by 9 by 2 factorial, that is 9 delta x square by 2 plus f triple dash of x by 3 delta x power 3 that by 3 factorial, that is 3 power cube 3 power 3, that is 3 3s and 9 3s are 27 delta x cube by 3 factorial plus f of fourth dash power x I mean times f of fourth dash x into 3 delta x power 4, 3 3s are 9, 9 9s are 81, 81 delta x power 4 by 4 factorial, and f of x I plus 4, that is f of x plus 4 delta x, we are writing it as f of x and f of f dash of x at 4 delta x, I mean f of f dash of x into 4 delta x plus f double dash of x into 4 delta x square by 2, that is 4 square into delta x square by 2 plus f triple dash of x into 4 delta x power 3 by 3 factorial plus f fourth power x into 4 delta x power 4 by 4 factorial. So basically it denotes that all these terms are written expanded by using Taylor's series. These terms were the ones that we got from the questions. That is, in this question it is fi plus 4, fi plus 3, fi plus 2, fi plus 1, fi is given. So we are going in that direction. And normally it is f triple dash of x is equal to f triple dash of x is equal to a naught one coefficient into fi plus 4 plus another coefficient into fi plus 3. Like for all the terms ranging from fi plus 4 to f of I, we are having some coefficients divided by delta x cube. So this is what we are writing it as here. That is, this would be equal f triple dash of x is equal to a naught f x plus f x of I plus 1 plus a1 f of x I plus 2 plus a2 f of x I plus 3 plus a3 f of x I plus 4 plus a4 f of xi. So basically divided by delta x cube. So this term on the LHS would be equal to, we should be evaluating. So can anyone tell how would you proceed this problem from here? This is a simple step. One simple step is here, or else everyone just think for a minute what would be the next step. So basically we would be substituting the values of x, f for xi plus 1 plus fxi plus 2 plus fxi plus 3 and fxi plus 4 from these expanded Taylor series terms and put it in this equation so that this equation becomes 1 by delta x cube, and we are substituting all these values. Since we are not having, like, we are taking delta x cube 1 by delta x cube common, there is no 1 by delta x cube, so we are multiplying 1 delta x cube with this, and so all other expansion terms we are given, and this like a naught, a1, a2, a3 and all the terms like fxi plus 1, fxi plus 2, fxi plus 3, fxi plus 4, and that is fxi. So next step, what we are doing is we are taking all the terms in separately. Like f of x we are taking common and identifying all the coefficients associated with f of x from this term and putting it together. And identifying f dash of x and bringing all the terms, all the coefficients for this term from this equation. Similar way, double dash of x, f triple dash of x, everything f fourth power of x, everything we are bringing and coefficients we are associating separately. And thereby, all the common terms are also removed from this. And we are writing this equation. So, from this, we would be knowing that we can it is f triple dash of x delta x cube. So we are just associating all the terms to 0 and thereby we would be getting it this form. Like this one is 0, this one is 0, because what we were doing is this whole term is equal to 0. The RHS side is 0. So we would be equating it to 0. Every term therefore is associated and equated to 0. The coefficients are put up and equated to 0 since only in this equation 3 power 3 factorial minus all these terms are given. 3 factorial becomes 6. So we are now having 5 different equations and number of unknowns is 5. So basically 5 equations with 5 unknowns, we can solve it, and on solving this we can see that it is coefficients of a0 is 9, a1 is minus 12, a2 is 7, a3 is minus 3 by 2, a4 is minus 5 by 2. So if f triple dash of x is basically this 1 by delta x cube power, into a0 fxi plus 1 plus a1 fxi plus 2, a3 a2 fxi plus 3 plus a3 fxi plus 4 plus a4 f of xi. So when we are substituting back the coefficients in this equation, we will be getting it as 9 f of xi plus 1 minus 12 f of xi plus 2 plus 7 f of xi plus 3 minus 3 by 2 plus f of xi plus 4 minus f by 5 by 2 f of xi. This 2 we can take it as a common and remove it, so that all other coefficients get multiplied by 2. So the coefficient uh, P was for f of I plus 1. So we need to know what is the coefficient for fi plus 1. This is 9. Since we are removing 2 as found in the original equation, it would be multiplied by 2, it is 18. So we have arrived at the answer, that is 18. So basically, I hope the steps are clear. Just take a minute to analyze it and process it. If there is any doubt, please put forward. So yeah, like how we did this problem, it is a quick thing. Like we have identified what are all the terms that are present in this f5 plus 4 to f5 are present. So we have first expanded all this and we have written the form f triple dash of x is equal to, we have written an equation with coefficients for each of the term present, and then we have substituted all the known values that we have written from the Taylor series expansion. We have substituted all those values in the original equation, and we have identified and grouped together the common terms and equated that to 0, like depending on the equation. Here we are equating it to 0, and we are getting 5 different equations, 5 with 5 unknowns. So on solving those, we are getting the 5 different coefficients present in the term, and we can say that the value of p in the original equation or the question that was asked was found to be 18. Like when we are taking 2 common, as in the question given here, it is 2 is put in the denominator. So similar manner, if we are solving, rewriting the equation, we will be getting it as, we'll be getting the desired answer. So we'll now move on to the next one. Before moving on to the next few questions, there are few terms that are found repetitive in the questions that are found after this. So we just uh, look into what are all those terms mean in, like we'll have a quick idea of what those terms mean, so that it would be easy for us to solve those questions. So Lax theorem, it is used for the analysis or convergence criteria. Before that, in Lax theorem, there are few terms like consistency, stability, convergence. All those terms we should know what they mean. So what is consistency? Do any one of you have any idea? Consistency of, here it is defined as a finite difference approximation is considered consistent if by reducing the mesh and time step size, the truncation error terms could be made to approach zero. In that case, the solution to the difference equation would approach the true solution to the partial differential equation. So what is meant by consistency is that when we are reducing the mesh size and the time step size, like we are going by very small meshes and very small time steps, in that case the truncation error would be vanished or made to be zero, so that the solution of the differential equation would be approaching the solution to the original PDE. This is known as consistency. What is then stability? A stability in a finite difference approximation is stable if the errors decay as the computation proceeds from one marching step to the next. Stability of finite difference approximation is assessed using one Newman stability analysis. What is stability is that we would be running the simulations for a long period of time. So at one point we should be getting the stable results. That what that means is that the errors should be reducing as we are going forward with increasing time step. That is when we are marching a step to the one step to the next in time interval, the round of error, the truncation error, all the errors should be reducing and it should approach zero. It is should be decaying. That is known as stability. Stability is analyzed using one Newman stability analysis. What is convergence? Convergence means that solution to the finite difference approximation approaches true solution of the partial differential equation. When the mesh is refined of course, the finite difference formulation must have the same set of initial and boundary conditions. Convergence is that the finite difference approximation solution from this finite difference approximation should be somewhat approaching the true solution of the partial differential equation. That is, convergence is that we will be having a true solution to the partial differential equation that we are considering. For analysis purpose, we are converting it to the algebraic equation or using finite difference approximation and getting one solution from this. When the solution is approaching the true solution of the partial differential equation, we know that the convergence is criteria is met. So these are all the terms like consistency, stability and convergence are the terms used in Lax theorem. So what is the importance of Lax theorem? Lax theorem, Lax equivalence theorem states that a finite difference approximation for a properly posed partial differential equation satisfying consistency and stability that is truncation error is approaching zero when time step is reduced and mesh size goes to zero, and stability error goes on diminishing from time step to time step possess necessary and sufficient conditions for convergence. That is, it is stating that we will be looking how the convergence is achieved. Therefore, Lang's theorem states that for the finite difference approximation for a properly posed partial differential equation, when if in case it satisfies the consistency and the stability, uh, it possesses sufficient conditions so that the convergence criteria would automatically be met. That is, when consistency and stability condition criteria are met, convergence criteria would be met. That is what Lax theorem states. What is consistency? Consistency is that when we are reducing the mesh and time step size, the truncation error would be approaching zero. That is, differential equation would approach true solution. Stability is that when the computation proceeds from increase through increasing time steps, it is that round of error, truncation error are all decreased in step-by-step manner. So when consistency and stability is met, the convergence criteria is also met. Convergence criteria states that the finite differential approximations true solution would be approaching the true solution of the partial differential equation. So it is that Lax theorem is that when it satisfies consistency and stability, the convergence criteria is also met. So we'll see problems associated with the Lax theorem and stability, convergence, everything from in next few problems. Before that, let us take a 5 minutes break. We'll meet by 7:01 sharp. So we'll move on to question 8. In question 8, it is asked convergence condition is about the equivalence between exact and the numerical solution of the partial differential equation, exact solution, the numerical solution of the discretized equation, exact partial differential equation and the discretized equation, none of the above. So basically we have seen what the convergence condition is now. It is basically the exact and the numerical solution of the partial differential equation. Equivalence between when we say the convergence is achieved, that the exact solution of the partial differential equation is there and the numerical solution that we are arriving at would be there when both of the when there is equivalence between both of them, we would say convergence condition is met. And that is the exact and the numerical solution of the partial differential equation is known as equivalence between the exact and the numerical solution of the partial differential equation is known as convergence. Convergence condition is about the equivalence between exact solution and the numerical solution of the partial differential equation. So the answer to this question is option 1. In question 9, which of the following statements is true about differencing schemes? Inconsistent schemes cannot be stable. For stable schemes, inconsistency does not matter. An inconsistent scheme will not yield the correct solution. Stable scheme will lead to the converged solution within truncation errors. So it is asked that which of the following statements is true about the differencing scheme. First of all, when the scheme is inconsistent, it will not be yielding the correct solution. Stable schemes will lead, only this option 3 is right. Inconsistent schemes cannot be stable. For stable schemes, inconsistency does not matter. It is not true. Like stable schemes will lead to converged solution within truncation error. No, the answer to this question is inconsistent scheme will not yield the correct solution. It is true always. That is, inconsistent scheme will not yield the correct solution, whatever be the case. So answer to the question 10 is, question 9 we have solved, and question 10 is, a grid independent solution is expected to agree with uh, the analytical solution of the partial differential equation, exact solution of the discretized equation, both of the above, neither of the above. Can anyone say what is grid independent solution? Because in this problem it is asked about grid independent solution. Before moving on to the problem, we should be knowing what grid independent solution means. So basically grid independent solution is that it means that when we are changing the grid size, either refining it by decreasing it further or increasing it in smaller steps, it should not, the solution should not change. That is known as grid independent solution. The first statement or the second statement does not make any sense with this regard. That is the analytical solution of the partial differential equation or the exact solution of the discretized equation. No, it is not expected to agree with this. It is just expected to agree with the solution when the and remain the same when the grid sizes are changed. That is, solution does not vary significantly when the grids are refined further. This is known as grid independent solution. That is, so first statement or the second statement, both of these statements are basically wrong. Grid independent solution is expected to agree with, no, it is not agreeing with the analytical solution of the partial differential equation or the exact solution of the discretized equation. So basically, neither of the above is the correct answer. So these are all the 10 questions that were asked in the assignment problems in week 5. So now we move on to few other problems and interesting ones that are related to this week session, and we'll see how it can be solved. Uh, yeah. We'll move on to the question 11 of the next one. The truncation error in a finite difference expansion is minus dou square u by dou x square at I comma j into delta x minus 2 minus dou cube u by dou x cube at I comma j into delta x cube by 6. What is the order of accuracy of the finite difference equation? This question is a very simpler one. So can anyone say the answer? Like if the truncation error to a specific problem which is approximated using finite difference scheme is this one. What is the order of accuracy of the finite difference equation? This one is a very simpler one. Anyone can attempt it. So what does truncation error means? All those terms that are ignored in the from the Taylor series expansion or from the origin, like all those terms are with higher power that are ignored when using the differential schemes. So the order of accuracy depends on the truncation terms in the truncation error. So the power of the first term in the truncation error denotes the order of the accuracy. So what is the first term in this? Uh, this is the truncation error. The truncation error in a finite difference expansion is given by this. That is dou square u by dou x square into delta x by 2 minus dou cube u by dou x cube at I comma j into delta x cube. So this is delta x and this is delta x cube. What is the order of accuracy of the finite difference equation? So the first term is this, that is the term with the lowest power. So since it is delta x, the order of accuracy is 1. So answer is 1, 2, minus 2, minus 1. So the answer to this problem is 1. That is answer is 1. That is because it is delta x is present in the truncation error term and that is the lowest power and it is given by 1. So we'll move on to question 12. In question 12, two grid points are given, that is u1 is equal to 0, u2 is equal to 5 and they are at a distance of 0.5 centimeter. So we'll see what the question is. Find dou u by dou r at point 1. This is point 1 using forward difference method. So answer to this is 4 options are given, that is 1000, 100, 500, 5000. So what is dou u by dou r at point 1 using forward difference method? Uh, uh, Please just don't see the answer or the solution and just try solving it because it is a simple substitution problem only. And let me know the answer or just you yourself solve and see, but don't see the answer. Okay, the answer to this problem is by using forward difference scheme. What is forward difference scheme? We use f of x plus delta x minus f of x by delta x is equal to dou f by dou x. So it is asked that dou u by dou r, it would be u x plus delta x minus u of x by delta x or dou u by dou x or something. So dou at this point it would be 5, that is x plus delta x, it is 5. At x it is 0. So dou u by dou x, u x plus delta x minus u of x 5 minus 2 divided by x delta x, that is 0.5. 5 minus 0 by 0.5. 0.5 is in centimeter, so we are converting it into meter. So it is 1000. Basically, this means that it is the simplest new problem, that is numerical problem denoting how finite difference for forward difference method works. We would be subtracting this term and this term and divided by this. This is what basically happens in when we are you going in grid approach. Number of grids would be there and we would know the values at the boundaries, and we would be marching forward, and we know, like, if we know this point, thereby we would be marching forward and calculate all the values at all the points. This is how this method works. And we'll now move on to question 13. So here five more problems are left. So we'll just have a thing like these are all very easy or easiest problems are only asked in the further questions. So when the questions are displayed, please take a minute to understand uh, how all the question is, what is asked in the question, and see the options and identify which one is the correct answer. So it would be a practice for you people also. Thereby we can see, like, since these are not many tough questions, we can we'll see how to solve. It would be helpful for us. So the question 13, it is asked like, Lack's theorem states that convergence is assured for well-posed linear initial value problems. Stability is assured for well-posed linear initial value problems. Consistency and stability are sufficient for convergence of for a well-posed linear initial value problem. None of the above. So, uh, just we can just reflect back what we saw in Lack's theorem 3 slides back. It was that consistency and stability are sufficient condition for convergence. So what is consistency? What is stability? What is convergence? Just try to recollect that and we are good to go in the Lack's theorem. So okay, this is what we meant by consistency, stability, and convergence. Consistency is that when we are reducing the mesh size and the time step, if the truncation error is made to approach zero, this is known as consistency. Stability is one if the errors are made to approach zero, or errors are made to decay as the computation proceeds from one step to the next time step, that is known as stability. Convergence is that when the true solution is approaching the true solution of the partial differential equation, that is known as convergence. Lack's theorem, what does it state? It states that consistency and stability are sufficient condition for the convergence. So we'll just move on to the question 13 and see what was asked in that. Oh, I mean, what are all the statements present, and so basically it is that convergence is assured for well-posed linear initial value problems. No, it is not assured. I mean, Lack's theorem does not deal with that. It although deals with convergence, it does not mean that it is assured, and stability is assured for well-posed linear initial value problems. Although well-posedness is a criteria we are looking forward. We saw well-posed problems in the last session also. It is not stated by the Lack's theorem, whereas consistency and stability are sufficient for convergence for well-posed linear initial value problems. Lack's theorem states only this, that is, for in order to achieve convergence, consistency and stability are sufficient. So we'll move on to the problem. I hope this is clear from the Lack's theorem. We'll move on to problem 14. For the expansion given by equation A to be convergent, Which of the following conditions needs to be satisfied? For the expansion given by equation A to be convergent, which of the following condition needs to be satisfied? So the equation A is that, okay, we are given an equation that is f of x plus delta x is equal to f of x plus a df by dx plus b d square f by dx square plus c d cube f by dx cube plus d power f by dx power 4 plus e d phi f by dx power 5. So this is the expansion of a in terms expansion given up to the fifth derivative in Taylor's series. So we'll see which of the condition needs to be satisfied for it to be true. Small delta x, f to be continuous, f to be differentiable. So Taylor's series expansion is only true then the delta x is very small. Otherwise, think of a problem where we are given this line. In order to know the value at this point, or else like think it like this, some curve. To get the value at this point and this point, if we are using going by Taylor series expansion, if the delta x is considered it is line like this, a curve or a sine wave or something. If we are using Taylor series expansion and we are using only 1-2 points where zx is very large, it cannot be used, right? Like with only 2 points, it would be giving a straight line, not a curve. So small delta x is very much needed. And second option is f to be continuous. Obviously, the function should be continuous because we are using all these terms like df by dx, d square f by dx square. So, in order to get the value at every point, we expect the function to be continuous. And the third one is f to be differentiable. So, when we are dealing with continuous points, since we are dealing with derivatives and Taylor series expansion, we are need this f to be differentiable. So, for the expansion given by equation A to be convergent, which of the following condition needs to be satisfied? So, f of x plus delta x is equal to f of x plus a times dou f by dou x plus b times dou square f by dou x square plus c times dou cube f by dou x cube plus c times dou power 4 x by f by dou x power 4 plus e times dou power 5 f by dou x power 5. So all the three like small delta x, f is continuous, f is differentiable, all three needs to be satisfied to get into the convergence criteria. For the equation given by this to be convergent, we need all three to be needed. One is sufficient, one is required, but one is not sufficient. Two is sufficient, same way two is required, but it is not sufficient. Three alone is sufficient, false. All three are necessary. This is the right answer. We need all three. That is smaller delta x, f to be continuous, and f to be differentiable. So we'll just move. I hope this is clear. We'll now move on to answer is option 4. That is all three are necessary. Small delta x, f is continuous, f is differentiable. We'll see the question 15. This one is a very simple question. You may consider the equation dou u by dou y at I comma j is equal to uij minus uij minus 1 by delta y formulated using Taylor's series expansion. Find the type of equation. I guess anyone can say this without giving the option. So, is there anyone from who wants to answer this question? We'll just wait a minute. If anyone is willing to answer, they can answer. Without the options, it is possible. It is asked like dou u by dou y at I comma j is equal to uij minus uij minus 1 by delta y. So basically this what is the type of equation, or we can say what is the type of schemes that is used in this equation, in this in the conversion of partial derivative differential equation into algebraic equation. So the answer is actually we can see that we are marching in the y. Dou u by dou y is asked, and at point I comma j it is asked. So basically it is delta y is given. From this it is seen that uij minus uij minus 1, that is a present point, and the one point that is one step before or backwards is given. So it is backward difference scheme. We'll see the options, and we have neglected every other term. So basically this we know to be first order uh, expressions. So it is first order forward difference, first order rearward difference, second order forward difference, second order rearward difference. We are neglecting only the a term starting from dou square u by dou x square dou y square, and that too the associate terms would become del y when we are dividing the entire equation by delta y. So basically it is a first order scheme, not second order scheme. So these two options are obviously eliminated. So uij minus uij minus 1, it is since we are going one step, we are going one step back. This is known as forward, first order rearward difference. So I hope this is clear. We'll now move on to next question. So the answer to this is option 2, that is first order rearward difference or backward difference, both are same. First order backward difference. So now we'll move on to question 16. Consider the following expansion of function f about point I. F of x plus delta x is equal to f of x plus a df by dx plus b d square f by dx square plus c d cube f by dx cube plus d power 4 by dx power 4 plus e d phi f by dx power 5. This is the equation A. Consider the following expansion of function f about point I. The value of b in equation A is, what is the value of b in this equation? This we know is the Taylor series expansion. So what would be the value of b in this equation? Can anyone say the answer? The question is a very straightforward question. It is given a Taylor series expansion of fx plus delta x with 5 derivatives, 5 terms. So it is asked what is the value of b in equation A. So if we look into Taylor series expansion, it would be fx plus delta x is equal to f of x plus df by dx into delta x plus d square f by dx square into delta x square by 2 factorial plus d cube f by dx cube into delta x cube by 3 factorial and so on. So basically what the value of b in those equations would be. So we'll see the options first and then decide. The first one is 2 factorial, second one is 1 by 2 factorial, and option 3 it is 1 by 4. Option 4 it is none of the above. So from this option, if you can say it is fine. Like anyone wants to attempt this question? So yeah, it is answer would be B is, since it is B is delta x square by 2 factorial. Then none of the above would be the correct answer. So we will see what the answer is. Answer should be option 4. Answer is option 4. It is 1 by 2 factorial into delta x square. This is given, but only half of the terms are given. It is delta x square by 2 factorial. So which of the following terms represent the central difference approximation of dou u by dou x? There are four different diagrams given, and it is asked that which of the following diagrams represent the central difference approximation of dou u by dou x. So basically, what is the central difference approximation of dou u by dou x at I? We have seen the forward different schemes like forward difference, backward difference, and central difference. So first, can anyone say how these three schemes differ in their approach? Okay, so in forward difference scheme, we would be using the current point and the point one point and the next point. For this one, I am saying for dou u by dou x, that is the first order derivative. So it would be dou u by dou x would be ui plus 1 minus ui would be divided by delta x. That would give us first order scheme, and the second order scheme would be backward difference scheme would be ui minus ui minus 1 divided by delta x, and the central difference scheme would be ui plus 1 minus ui minus 1 divided by 2 times of delta x. So from this expression, in this question, it is asked for the central difference approximation of dou u by dou x. So it is like ui plus 1 minus ui minus 1 divided by 2 times of delta x. From this, it is understandable. So if can anyone identify, like answer to this question is obviously given here. It is option 4, but if anyone of you want to explain this, it is fine. Like how we have identified it to be 4. So basically it is that in the first one it is I and I minus 1 points are chosen. So it is kind of a backward approach. And in option 2 also I and I minus 1 points are chosen. It is backward approach or backward scheme. In option 3 it is I and I plus 1. That is I plus 1 and I. Here we can see clearly this is I minus 2, this is I minus 1, this is I plus 1, this is I plus 2. So from this also it is clearly seen that it is I plus 1 and this is I. These 2 points are chosen. So it is like for a different scheme. Basically I plus 1 and I. But in the option 4, that is the last diagram, the points that are chosen are I minus 1 and I plus 1. The line is passing through this. What this diagram basically denotes is that this is a curve that we want to are using, and the points that we are using for the calculation in different schemes is that this is obviously the curve, original PDE, and we are going in a step by step manner in this way. Like there are different approaches, and the last one is the central difference scheme where we are using I plus 1 and the I minus 1 term. So it is like this is the correct answer there. Therefore, this is the correct answer. So central difference scheme is passing through ui plus 1 and ui minus 1 divided by 2 times of delta x. So answer is option 4. So these are all the questions for today's session. In today's session, we saw the finite difference approximations followed by a few problems, very few problems on stability, convergence, consistency, and so on. Like Lax theorem, main focus was on finite difference approximation, and by majorly focusing on Taylor series and how it is used for different partial derivatives, expansion, and with order of accuracy. These are all the topics that we learned in today's session. If there is any doubt in today's session, please let me know. We can take any questions.
Thank you, ma'am. I
Yeah.
just joined it because of some network issue. Thank you very much, ma'am. No
Oh,
doubt, ma'am.
okay, okay. And did you attend, like, from which one you were able to see?
Ma'am, for the last 3 or 4 problems, I attended, ma'am. I just finished my work and I was on travel and not able to get the tower properly. So at one place I am standing and listening the class. So last 4 problems I attended, ma'am. It was okay, ma'am. Thank you, ma'am.
Okay, okay. I mean, I'll just give a quick recap then for you. Like, not.
Ah, no
Mm,
problem. That I think it is uploaded in YouTube.
yeah, it is there in
The link
YouTube
is
also.
given. We will go through, ma'am. Thank you, ma'am.
Okay, okay, okay. Thank you.
Thank you. Ma'am, I think other person also left, ma'am. Only
Oh,
myself alone here, ma'am. Maybe
okay.
wind up, ma'am.
Yeah, yeah, we'll wind up the session. Yeah. Thank you. Thank you for attending today's session. We'll see. We'll meet every one of you in the next session. That is on next Tuesday at the same time, 6 to 8 p.m. What? This is just a quick thing of what we saw in today's session. With this, we'll close the session. Like in today's session, we saw the basic concepts of